Hello, it's Keith here, and this is lesson 4 of my YQuest assembly tutorials. Now, in this we're looking at the source code for the YQuest game, which you can see here, and today we're going to be looking at the Commodore 64 version. So, YQuest is this little free game. It's a remake of a DOS game I used to own called Yquest, which I believe was some kind of remake of another game as well. So anyway, this is what we're going to be looking at today. It's free and open source. You can go ahead and download it from my website if you wish, and you're welcome to use the code for whatever you want. Now, the game code itself was based on the Simple series, which we covered in a previous tutorial on this channel. That was where we got a smiley face to move around with joystick controls. And the point I was trying to make with this game is that even though that was a relatively basic looking example, there's no reason you couldn't take that and create that into a legitimate game that you could quite rightly feel quite proud of. So as I say, you can take my code here and use that if it helps you in any way. I don't care if you use it commercially, you're welcome to do so. We're going to have a look at the source code for the platform specific stuff today, the Commodore 64 specific bits. Let's go over and let's have a look. Okay, so here is the source code for the game that you can see running today. Now I'm going to go through it all and we're going to just briefly discuss the bits that are Commodore 64 specific. There are other episodes for the common code. There's a lot of common code to all systems. We're not going to cover that today because obviously there's quite a bit of it. Okay. Now the first thing, we have some common definitions here which define the size of the screen. Some of these systems have different screens and the common code needs to work in different ways dependingly. Now another thing that's a problem is the resolution of the movement is different in some cases. Some systems are limited to 8x8 blocks, others can move at the pixel level. And the collision detection we need to simplify if we're not able to show the same visual representation that the code is actually calculating at. For example, if you've got two objects that are partially overlapping, but you can't actually draw that partial overlap because of the limitations of the screen. Now on the Commodore 64 version, I've actually halved the width of the graphics. Usually they're 8x8, but in this they are 4x8 because I'm using the full color mode. And that means that we're having to reduce the resolution of the collision detection accordingly. So we've got these to do that. We're using full color mode here. The code has been left in to work in 2-color mode, but I've not defined any sprites for it. So you'd have to change the sprite and maybe change some of the color code to make the game work in 2 colors. But the code that would turn the graphics on is still there. We've then got 0-page definitions for my temporary variables, a pointer for the sprite colors, because we need to use an extra bit of information, the bitmap information and the color information to build up the image on screen, and some user memory for the current objects and things to be stored in. We've got our initialization routine here for our program here. We've got our screen turning on routines here. You can see, as I say, the 2-color code is still there. Now we're remapping the screen here. Usually we'd be working at 2000, but this time we're actually remapping the screen and offsetting by 4000, so the screen base will be at memory address 6000, and the reason for that is the color graphics and the color font in this game, we're actually using up quite a lot of memory. So we're actually moving the screen around here. Our screen base is offset by 4000, so it would usually be at 2000, but now it's actually going to be at 6000. So that's what we're doing there. Now we'll see some changes in the code to represent that, and then we're defining our colors here and we're clearing the memory, and then this is the start of the game code itself. So we're initializing a new game here, setting the lives, clearing the sound and things, clearing the screen, and then we are drawing the title picture to the screen here. Title picture is at memory address title pick here, and we're using the sprite routines, calculating the address in RAM of the bitmap data, and then showing the sprites to the screen. Now our X coordinates are done in 4-pixel blocks, which is correct, but our Y coordinates are in lines, so we need to multiply by 8 with some bit shifts here, and then we are showing the sprite to the screen, repeating until the entire screen is drawn there. We're then showing some bits of text to the screen. We are just showing a fire message, the high score and the website address, and then we're waiting for fire before starting the first level. This is repeated for every new level as well. So we clear the screen, set the player back to the center, and we calculate the objects on the screen for the level, so the enemies, the mines, things like that. Here we've got a loop. This is affecting the speed of the game. We can speed it up or slow it down by changing this. X is used for any keys that are pressed. We're calculating the key presses with this routine here. We'll see that later. And we're storing any keys pressed in X here, and we're just looping to slow the game down a little bit. Here we're showing the text onto the screen, the remaining crystals, the lives, things like that. And here we're removing the player sprite from the screen. We've then got this key timeout. Now, if you hold down, up, down, left or right, the player's X will accelerate, or Y rather, sorry, the player's Y will accelerate and will become faster and faster, but we don't want that to happen too quickly. So if the player holds down up, we'll ignore the key being still pressed for a few ticks, and this key timeout deals with that. Then we've got detection, checking each of the directions, up, down, left and right, and we're changing the acceleration accordingly, the Y acceleration here and the X acceleration here, and we've got these common routines here to just alter the Y or X acceleration as required of the current object. IX is set to the player object here. So these are up, down, left and right. Here's the fire, this will fire a bullet. And we do have the option for a second fire which would stop movement. I don't think that actually works on the Commodore 64, but the code is still there anyway. Finally, we're saving the timeout if it's been changed. Up, down, left and right all set X to 5, which is the new timeout. And so that will stop the player from moving too quickly there. And then we're updating all of the game objects and we're just looping back to the top here. So this is the main program loop. You can see it's fairly small, but that's because all the common code is in here. Our clear screen routine is here. The screen has been offset to 6000 and the size is 2000 in hexadecimal. We're using this clear command to do that. Here we've got a print character routine. This will print the character in A to the screen. There's no characters below 32, so we're subtracting 32. We're calculating the sprite color here. We're using entry 16, there's 2 bytes per entry here. We'll see those later on. And then we're calculating the offset within the font of the character we want to show. That's a typo there. There's 8 bytes per character here. So we're multiplying up there, and then we're adding that to the font here, and then we're calculating the position to show the sprite. We're using the same sprite routine for the font and the graphics in this case. Our blank sprite routine here is just checking if the current object should be shown. A collision program greater than 250 is a dead object, so we would skip in that case. Otherwise, we're using the space of our font. Get sprite address is calculating the color entry here and storing that in 0-page entry Spurpunten here. And then it's multiplying up and calculating the sprite entry, adding the frame here. You've got the frame, there's 128 bytes per frame. So there's 16 sprites per bank, and there's 128 bytes per bank there. So we're just calculating that up. And so this is calculating the address to show a sprite to the screen. Do get sprite object gets the sprite number X and Y position from the 0-page IX. Now that would point to an object within the object array or the player object, and it gets all of the other parameters from there. So you can see we're getting the X position here. We're having to skip some bits of the X position because the internal calculations are higher resolution. They were designed for something like the Amstrad CPC, which is relatively high resolution. And so on a system like this where we're limited to relatively low resolution, we're just having to skip some bits here. And we're doing the same with the Y position here. We're just having to skip these 3 bits because we're moving in 8x8 chunks for simplicity of the screen. Show sprite here will calculate the screen position, the memory address, and then it will transfer the bytes of the bitmap data here until the bitmap is done, and then it does the same for the color information. We're using get col mempos, which will take an XY location and calculate the memory addresses of the 2 pieces of data for the 4 color information, and then we're transferring from the sprite palette using that pointer here, and we're transferring the colors to the screen as well. Get screen pos is here. It's been changed very slightly because the offset is now 6000 rather than the usual 2000. And we've got get col mempos, which calculates the color location. And again, this is now offset by 4000. So it's now 4400 rather than the regular 4000. But the color data at D800 is unchanged. It's not changed its memory location there. We've got our read controls dual here. This is just reading in from joystick 2. That's the one we're using by default. We've got a wait for fire routine here, and this updates the random numbers, reseeding effectively until fire is pressed and released. That's our debounce there. Here we've got our font. This is in native format, and our bitmap data again in native format. These don't contain any color information. The color information is just here. So this is 2 bytes using 3 nibbles. This nibble here is unused. And these are transferred to the memory addresses here and here to define the colors of a sprite that's being drawn. And we have 1 entry for the font here. And then all we've got is some color common information here. These are some routines I've written in the past that are handling various things. Now the reason that this entry is being used here, of course, is if we look at our character drawing routine here, we were loading 16*2 here. Y2, well, 2 bytes per entry here, and this is entry 16, that's why. So these are the colors. So this is effectively the player color, and this is effectively the font color, and these are the other sprites accordingly. And that's really all the code that made up this version of the game. So there we go. As I say, you're welcome to download this and have some fun with it if you can make any use of it, and if you want to make a commercial game with it and you manage to do that, then best of luck to you. So I would fully endorse you to do whatever you want with it. Anyway, I hope you've liked this. If you have, please like and subscribe. I'm going to be doing more stuff on the C64, and we're going to be doing lots more YQuest, because I've now ported YQuest to the 68000 series as well. So that's going to be coming along as well. So YQuest is it's really a sort of continuation of the idea with the Grime Z80 project, the Grime 6502 68000. We're now doing these little games again on different systems, but I've taken a bit of a different avenue with the design, because this time I'm basing on the Simple series, and so I'm porting that to other systems, whereas with Grime, it was actually one common code that was compiling onto lots of systems, and this time there's a platform-specific version module for each one instead. Anyway, hope you've enjoyed this. I hope you enjoy your programming, and I wish you all the best. Thanks for watching today, and goodbye.